double-slit experiment. A beam of electrons strikes a baffle with two narrow parallel slits in it, and then a screen.
When we do this experiment with the lights on, nothing unusual happens. The electrons form the same pattern on the screen that you would expect for spitballs or wads of gum or even tomatoes. But when we turn the lights off, something very surprising happens.
What one observes on the screen is a series of maxima and minima.
This series of maxima and minima is known as an interference pattern.
Maxima are places where electrons accumulate. Minima are places that they avoid. The interference pattern is what you'd expect to see if you sent waves, not particles, through the double slit.
What we observed in the double slit experiment is explained mathematically by Schrödinger's wave equation, which predicts exactly the observed interference pattern. But quantum theory doesn't tell us where the particle is as it goes through the slits.
The essential difference between classical and quantum physics is that in classical physics one can predict both the positions and the velocities of particles, whereas in quantum theory one can't predict either.
Information was in 1985 I came across a paper by the American physicist Richard Feynman in which he talked about the possibility of computers operating on quantum principles. And this came like a bolt from the blue for me, because up until that point I was more accustomed to thinking of information in very abstract terms. In the ordinary everyday world, it's difficult for us to separate the idea of information from content and meaning. But we can get an idea of why information is physical if we think about, for example, what we would do if we were asked to point to information. And we would always point to a piece of paper with marks upon it. We might point to an optical fiber. We might point to a hard disk. In the case of a hard disk, we can see that information really does have some physical content. For example, when you want to store some information on a hard disk, you have to pay real money. You have to go out and buy, say, a 100-gigabyte disk. It doesn't matter what the information actually is, but the fact that there's a certain physical quantity there that you pay real money for tells you that in reality information is physical. For example, I'm talking to you now. Information is being conveyed using sound. I could write a letter, and the information would be stored as ink and marks on paper. Once you get the idea that information is physical, you then begin to wonder whether the laws of physics either constrain how information can be processed, or, in the case of quantum physics, gives you a completely new mechanism for processing and communicating information.
A bit is a fundamental unit of information, of classical information. It is encapsulated into physical system which can have two states, either something which is on or off, something which is charged or discharged, or something which is here or there, or, in mathematical terms, a 0 or a 1. In the quantum world, we have quantum bits, or for short, qubits. And these qubits can be in superposition of being in 0 and 1 at the same time.
And it's the ability to manipulate the world at that level of quantum weirdness, of quantum superpositions, that enables us to do computational tasks in quantum mechanics that are impossible, or at least very difficult, using conventional computers.